Good morning. We're starting on Chapter 2 today. We're breaking Chapter 2 into two parts. The first part will deal with the question of chemical bonding, and then next week we will take up molecular bonding, ionic bonding, this sort of thing. So today we're going to mainly talk about electrons, and then next week we'll talk about actual chemical bonds. Chemical bonds, there are two types. There's an ionic bond and a covalent bond. Ionic bond involves removal of electron, one or more, and giving it to another. The atoms are then charged. You have a positive ion and a negative ion. They're attracted to one another, and we'll say more about this later. Covalent bonding, which we'll be talking about in detail next week, involves the sharing of electrons. The electrons no longer belong to one atom or the other, but they're shared between the two. Now, in order to talk about ionic bonding or covalent bonding, we have to understand where the electrons are in location to the atoms so we can tell how they're going to go together. Now, we're going to see that there are different configurations of electrons, and they're in what we call orbitals. An atomic orbital simply gives the probability that an electron is in that area of space. That means that the electron in, say, an s orbital is likely to be somewhere in this sphere. An electron in a p orbital is more likely to be somewhere in this dumbbell shape, and a d orbital gets more complex, and then there are f orbitals, which are just totally unbelievable. Um, Atomic orbitals, the s orbitals, are spherical. Here is a 1s orbital, and the electron is likely to be somewhere within that sphere. A 2s orbital is the same thing, only it's just large. P orbitals start to get a little strange. There are three different types of p orbitals, and they're described geometrically on a grid. And each orbital contains a maximum of 2 electrons. So a p orbital might have 1, it might have 2 electrons. D orbitals get even more complicated, and they have this configuration, but again, this is where the electron is most likely to be. And then there are f orbitals, which we're not going to talk about, but I thought I'd throw them in just to let you know that things get much, much stranger than you first imagined. Now, there are rules that we have discovered about how orbitals get electrons. And this is called the Pauli principle, named after the gentleman that discovered this. Each orbital can hold at most 2 electrons. So you could have, at the bottom, you could have a p orbital that has no electrons. You could have a p orbital that has 1 electron, or a p orbital that has 2 electrons. And we're going to see that there are other principles involved in filling these orbitals also. But each orbital can only have up to 2 electrons. And then there's the Aufbau principle, and that's the order of filling of atomic orbitals. It comes from the German for building up or construction. So what this means is that the electrons will first go in the 1s orbital, then in the 2s. After the 2s is filled, the 2p will be filled. 1 electron going into each of the p orbitals. 4th, 5th, and 6th electrons will go back into those then. Then the 3s and the 3p and the 4s, everything's making sense. You've got the electron shells full completely. But then there's the 3d. Before we get to the 4p, we have to fill the 3d electrons. So this is a little bit unusual. Then we go 4p, 5s, 4d, no, wait a minute, and then 5p, 6s, and then the 4f. So pretty quickly things get complicated, but this explains how and why some of the elements behave the way they do. I don't know that we're going to get into that, but it gets a little see. Okay, where do the electrons go? Here's our nucleus, positively charged. The electrons go around it, and we can consider shells. 2 electrons, 8 electrons, 8 electrons. These represent the electron distributions of the first set of elements. The 2 electrons would be 1s electron. The second shell is the 2s electrons, and up to 6 p electrons, and the same way with the third shell. And then after that it gets, like I said, it gets a little messy. Okay, here are the electron shells for the first 10, 12, 15, however, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 22, 14, 15, 16, 17, 18, 19, 20. The first 20 elements, and we notice that they're filling one by one. The hydrogen has 1 electron. Helium has 2 electrons in the 1s. Lithium has 2 electrons in the 1s, 1 in the 2s. Beryllium, 2 and 2. Boron, following the Aufbau principle, 2 and 2, and then we begin to fill the p orbitals. We get to neon, we have filled the 2 p orbitals, and we start on the 3s, and so forth. So this gives you the electron distribution of the first 20 or so elements. Now, again, we can see hydrogen has 1, helium has 2, lithium 2 in the 1s, and 1 in the 2s. So the 2s orbital is half full, the 1s orbital is all the way full. Beryllium has an atomic number of 4, 2 electrons in the 1s, so it's full, 2 electrons in the 2s, so that too is full. Boron, atomic number 5, 2 in the 1s, 2 in the 2s, 1 electron in the 2p orbital. So there's one of the 2p orbitals is half full, and the other 2 are empty. Carbon, 2 in the 1s, 2 in the 2s, 2 electrons in the 2p. Now notice that there are 3 different p orbitals, 1 electron in one, 1 electron in the other, and the third one is empty. And that's the way they fill. They fill so that you get maximum distribution of electrons. Now if we look at the electron configurations of the noble gases, this is the column of materials that is on the extreme right hand side of the periodic table. Remember that they're called either noble gases or inert gases because they don't react. The outer orbital is filled in each case, and this is why they're not reactive. Helium, 1s2, so the outer orbitals are filled. Neon, 1s2, 2p6. Can't read the print very well, can you? Argon, 3p6. Krypton, 4p6, 5p6, 6p6 for radon. So all of these have their outer orbitals filled. Now that means that they're very stable. That means that they're quite unreactive. On the other hand, if we look at the alkali metals, the group over on the extreme left-hand side, we see that lithium has a 2s1, and so that can be very reactive. Sodium, a 3s1. These electrons can come off very easily to form positive ions. And you notice a little shorthand that we're using. Lithium has the helium shell and then a 2s1. Potassium has the argon shell and then a 4s1. So this is a way of just abbreviating things, saying that potassium has all of the electrons in argon plus 1. The halogens over on the right hand side, right before you get to the noble gases or the inert gases, all of the halogens have 5p electrons, so that If they got one more, they would have a noble gas configuration. So they all have 5p electrons and can take in one more. Okay. The alkali metals all have one s electron present. It's very easy to give this s electron up and to form a positive ion. The halogens have one empty space in a p orbital. They have 5p electrons. It's much easier for them to accept one electron, giving them a p6 configuration, and then they would form a negative ion, and we'll make use of that later. Okay, here's some of the electron configurations that we see. Here's carbon. Carbon has the nucleus, has 2 electrons and 4 in the outer shell, and we'll be talking a lot about carbon in various times. Okay, that's it. Review the chapter, go over it, try to get your head around the fact that these electrons are doing things that we don't normally expect them to do, but there are strange things in the world, and this is just part of them. So we will see you later.